he uses it as an initial condition for his scalar boundary value.
Well, okay, so this is a magnetic vector. This is
That's the scalar potential,
right.
right? Let's not think about the scalar potential.
Okay.
Let's worry about the vector potential. Because it turns out that the scalar potential only works in a small number of cases.
Right. No, I don't think we have enough information to take a gradient. Let's use symmetry.
There's one.
Here's what I'm thinking. I'm thinking that when you take, there's enough information to take a gradient if you make a symmetry argument. Right? And you say, the field along this axis is only along the z direction, then you can go ahead and take a gradient.
Right, because then you take the gradient only concerning yourself with the z direction. And
Yes.
coming out.
Yeah.
Please don't put something like that.
It'll be fun.
That would drive me crazy.
Put it on using
Actually, I'm pretty sure that this will not work. Yeah, you need to have the spatial terms in order to use the vector potential to calculate the magnetic field even on the axis, even though we know it's z.
Well, there are
Because this will come
several-
out to be 0. This all by itself is 0.
Right, okay.
Because there is no theta or phi dependence in there. And in order to get a z component, we have to be able to take the derivative with respect to theta or phi. Because there aren't any other derivatives there later, I think.
But that is the correct potential along the z-axis.
That is the correct potential on the z-axis. And you can be sure that when Ohanian says, we won't do this because it's a little messy, it's a little more than a little messy.
No, he says this is very messy.
No.
It's very
Super very.
Because things are simple and it's very good. Oh my god.
Okay. I haven't had any questions from that side of the room beyond Cal. How about back? Yeah.
So nothing on like RLC, also in circuits and stuff? Because that was in the chapter.
What course are we in? No. Oh, because we're covered inductors, and we have capacitors. No.
So it's
Mentioned.
I probably should, but don't, do AC circuits in this course. Because, although, yeah, because you guys got cheated by Stoller.
Yes, we're going to do AC circuits.
I think that's cheating. AC circuits with impedance is a lovely thing to behold.
Yeah, I remember. I remember learning it.
The time to learn it is sort of now, actually, after you should, at this point after quantum physics, be really comfortable with e to the I anything,
Yeah.
right? And with Fourier transforms.
No.
You
Well-
should be. And once you're comfortable with that arithmetic, suddenly AC circuits becomes a breeze. I'm going to spend a lecture on AC circuits.
But as far as the second exam goes, we shouldn't look for it.
What?
We shouldn't look for AC circuits on this exam.
Not on this example, no. Next class, someone needs Ryan to remind me that I promised to talk about impedance and AC circuits. Like you've learned all about reactance.
Well, I also read it. I also read more.
You read it where?
No, maybe in another place. I read.
Yeah, no.
That didn't-
We have, I split my time in this. Yeah, we got the basics. We're gonna do, potential in, fields where the charge is moving, and that's fairly complex. And then after that, it's applications. And, I like to do the applications because, you've learned all this theory, But what you're actually going to do is apply it at some point. And so it's good to see the applications. I hope you'll apply. Yeah, otherwise you're a theorist and you're useless to me.
Do we have to know
No.
the last thing?
No, I decided to, I think someone asked the question and I said, I think it was Leah. And I said that, we'll put that off. Do we have a third exam in this course or we just have two exams and a final?
Just 2 exams and final.
Right, okay. Finals, you're chock-a-block full.
Is the final going to be cumulative?
Yes.
Well, what we do is
But-
make it cumulative, so emphasize the material.
It's going to be weighted to the material on the letter.
It's like a harder stuff.
I got the first half is essentially same thing. Like all the equations, transactions. It's not really like it's.
What it's gonna use is basically going to have the 30.
That's sort of our corner.
Yeah, it's hard to forget, is that what you're saying?
Yeah.
Yeah, so easy.
The anti-curl for the B field.
Let me think about that.
Is that's the B field in terms of J with that's as far as with subbing in the fact that J is also equal to the cross B.
So that's A.
I was thinking more about some sort of 3x3 matrix that had an operation in each of the terms of the matrix that would return the anti-curl.
So each matrix will have
An integral in it.
Why not? It might be impossible because it isn't actually defined in terms of the Levi-Euclid. It's a pseudo tensor, so it doesn't really obey any of the properties of.
It doesn't, you're right, so it might not be able to do that.
So in general, it might not be possible, right?
Yeah, I'm going to leave that for you to work out. I'll suggest it for the next math modeling contest.
The class topics you listed off earlier in the lecture, earlier in the
This
offset,
section, yeah.
Can you upload those to,
Camera.
I can try.
can you upload that?
You're asking, so he can put that up, all right?
Sure.
Josh, it's all on his course schedule, except for like all these install for all.
You can turn that off now, because I won't say.